So I'd like to tell you about temperature of the universe. And if you Google, its answer is 2.7 Kelvin. Well, it's the temperature of photons, but of course, the universe contains not only photons, but also a bunch of other things. If you, for example, think about cosmic neutrino background, temperature is supposed to be 1.9 Kelvin. And then if you then Google gas temperature of the universe, they know the answer already. Ah, so it's our work. So I'm very glad. Yeah, yeah. Look at this. They converted Kelvin into degrees, right? Exactly. Yeah. Yeah, yeah. So that's what we're going to talk about. And uh, this presentation is based on 3 papers. So first of all, how hot is the largest scale structure of the universe? How was it before? So we're going to tell you about thermal history of gas in the universe. Then once we measure the thermal energy, you can ask, where does that come from, right? Is energy conserved? Answer is yes, and I will tell you how we did that. Then finally, is this just beautiful physics, or is it just useful for anything, right? And I just would like to say something about that and conclude. So cosmic energy inventory is the Masataka Fukugita's favorite subject. And he basically, spent most of his career. So he's done a lot of other things, but he really wanted to get the table of energy densities of all components in the universe. Now, everybody knows that mean energy density and mean mass density is omega model 0.3, omega model 0.05, but we don't know what is omega for the thermal energy, right? So this kind of properties is useful. And for example, if you ask Masataka, he'll tell you, dark sector, primitive baryon rest mass, neutron stars, and they're all omegas all here. And it is this paper, well, actually previous paper preceding this, that defined missing baryon problem. Right? So you actually count, you discover something is missing. Right? So this is kind of very, very useful thing. And then the list goes on, right? And then 10 to the minus 6.5, and these things, right? But there's no thermal energy density. Okay, so let's go out and measure this. Yeah. All right. So let me define thermal energy by kBT rather than 3/2 kBT. I mean, just matter of convention. So basically, what I'm measuring is a thermal pressure, and I pretend that thermal pressure defines the thermal energy density. If you don't like this definition, just multiply by 3/2. It's up to you. So this omega is the co-moving energy density in thermal energy divided by critical density of the universe. Yep. All right. Then let's do order of magnitude estimation, right? That's what we're supposed to do always. So thermal energy density is given by, or the pressure, thermal pressure is given by mass density in gas times the one-dimensional velocity dispersion in the larger scale structure. So let's plug in something like sigma 200 kilometers per second, pretty decent value for lambda CDM cosmology, omega gas of 0.05. Let's say all the baryons are ionized and thermalized. Then you get something like 2 times 10 minus 8. Our measurement is 2 times 10 minus 8. Okay, so it's kind of nice. I mean, in detail, actually, this isn't quite a correct way of estimating it, but that's what all our magnitude estimation should do anyway. So it's very easy to interpret, right? What's going on, and but in detail, it's very interesting. You can really think about energy conservation, energy conversion in the whole universe. All right, so we're going to use thermal Sunyaev-Zerodovich effect to do this measurement.
If you interpret that 200 kilometers a second just naively like that, what temperature does that correspond to?
2 million degrees. Yeah. All right, so you have the, so this is the still W map, okay? Then you go back in the light cone of your measurement, and farther you look, the more distant past. And this is when the universe became transparent to photons. Then photons now pretty much free stream, but sometimes they are deflected gravitationally by gravitational lensing. And also they sometimes hit cosmic structures, and their photons are modified by Compton scattering that happens in the hot gas in the universe. Yeah, so it is this that we're going to use to measure thermal history. So you have CME photon that gets hit by energetic electrons inside of hot plasma. Then you get blue shift, Comptonize photon, which we measure by radio telescope. That's called Sunyaev-Zeldovich effect. And this is the CMB spectrum. These data points are Phylas measurements. Ancient Phylas measurement. As usual, I multiply the error bars by 200 times, right? So it shows you how precise this black body spectrum is. Now, when you have this Compton scattering, the low energy photons are upscattered to high energy. And because number density of photons has to be conserved, you have a dip in the low frequency, and you have the increment in high frequency. So that is called Sunyaev-Zeldovich effect. And its magnitude is characterized by something called dimensionless Compton Y parameter. Bigger this, the more thermal pressure of gas. So if you subtract the CMB, right? So now these are real error bars, not multiplied by 200. Then you get this kind of decrement in intensity in low frequency and increment in high frequency, right? It's negative relative to CMB, but this is not absorption. Okay, this is scattering. So this comped up scattered from here to there. Yeah. All right. So indeed, this is the real data of Planck measurement. Planck has many bands, 44, 70 gigahertz, 100 gigahertz, 143, 217, 353, 544, 545. And indeed, this is the one of the Bell class, a very rich cluster of galaxies that contains lots of hot gas. And yeah, as promised, decrement first, and then increment. Yeah. So using this, you can make a map of all hot gas in the universe in projection. Okay. You don't have redshift information here, but you can do some technique called tomography that I'm going to present to get redshift information as well. So where's the galaxy cluster? So let's see. Astronomers typically believe that for some mysterious reasons, the galaxies in galaxy cluster are red. Okay, so what you do then is to look at concentration of red galaxies, like this. Zoom in, and you see beautiful gravitational lensing arcs. This is the ground-based telescope, Subaru telescope, Japan's flagship telescope made by Mitsubishi. It's like a tank. It's really, really, very expensive, but also very, very well-made telescope. But if you wanted to really see clearly what these gravitational lensing arcs are doing, for example, you have to go to space. That's HST. Yeah, very, very nice. Now, this galaxy cluster contains lots of hot gas, which is not visible in optical. One of the first things that the X-ray astronomers discovered by launching X-ray telescope into space was that galaxy cluster contains a gigantic amount of hot gas. In a way, this is dark matter. No? In the optical, it's completely invisible. So this was dark matter, dark baryons that shines in X-ray because this temperature of this gas is very, very hot. Yeah, 10 to the 8 kelvins, 10 to the 7, 10 to the 8 kelvins, 100 million degrees. Yeah. Now, if you go to microwave, that's it, right? And I'm very proud of this image because we took this using ALMA. It's a first image of galaxy cluster in microwave using ALMA. 5 arc-second resolution, highest ever achieved for this kind of thing. And for the first time, angular resolution of microwave matched angular resolution of X-ray. So you can really do all kinds of exciting science with that. For example, right? So we have optical galaxies, X-ray hot gas, and SZ is hot gas as well. But because X-ray is emitted by collision of protons and electrons, so Bremsstrahlung, its intensity is proportional to density square. So it's very sensitive to clumpy medium, and it's very, very centrally concentrated. On the other hand, Sunyaev-Zeldovich effect is directly proportional to pressure. It's number density times temperature. So they probe gas in somewhat different ways. And so X-ray data are, for example, more sensitive to clumpiness of gas. And SZ is more sensitive to very high temperature, highly pressured regions. For example, X-ray telescopes are band limited, which means that they are completely blind to temperature above 20 keV, for example. But SZ is completely sensitive to arbitrary temperature values. So look at this. X-ray image of RxJ 13147 minus 1145. And that's the SZ map, right? So for the first time, we can actually compare two images at the same resolution. And this is density view. This is a pressure view, okay? Then I subtract. So let's say I average the intensity here and subtract from this map to look at fine structures in the cluster. And you see this very funny dipolar image of density. Okay, what that means is that there's some clump coming in that gravitationally perturbed the central gas concentration, and central gas entire thing moved. Right? It's called sloshing. So this part has less gas, this part has more gas. So what that means is because of the perturber, central parts shifted to the north, and they actually oscillate. But if you look at the SZ, nothing, right? What does that mean? That means this sloshing is subsonic, right? It doesn't change pressure. It just, and this you never knew unless you use SZ, right? So, but what about this? It's a shock region. So a perturber came back, and then shock heated here. So that's the kind of picture that we have in our mind. But the detailed comparison between SZ and X-ray reveals many things. This is another example. Phoenix cluster, deeply cooling galaxy cluster. Inside of this, it's a gigantic star-forming region due to so-called cooling flow. Cool the gas toward the center. Now you subtract the mean component. Again, X-ray is doing something complicated. SZ, nothing. So this cluster is very, very stable. No, something called cool core cluster, which hasn't really experienced much merger in recent times. So gas sits there and cools like crazy. Now we have, by now, 4 galaxy clusters imaged by ALMA, all 5 arc seconds angular resolution. And we have evolution of gas from 0 to 1, 0.1, 0.6, 0.45. And what you're seeing here is that early on, it's a mess. Right? So you have these collisions of galaxy clusters, halos, perturbing gas, and it's a big mess. But as time goes by, they started to really assemble and grow as the standalone gigantic galaxy cluster. And then they look very, very regular by this time. Yeah, that's what you're saying. ALMA is super powerful. Atacama Cosmology Telescope, right? Beautiful telescope, has 1 minute angular resolution, and that would be entire. So this will be 1 blob. Yeah. Okay, good. So how hot is the largest scale structure of the universe? Because what I just talked about is the individual objects. So let's do this for the entire universe, right? So to do this, you use multi-frequency technique of the Planck full sky data to create full sky maps of the electron pressure. So this is all gas there is. Yeah? No gas is left behind. Everything is in there. For example, this is a coma cluster. Yeah, so that's very nice. Then, but limitation of this data is that this all hot gas in projection, you don't have the information of the depth, right? You don't know where this gas actually sits in the radial coordinates. Therefore, what we do is a tomography. Namely, we have objects, galaxies with known redshifts. Then we cross-correlate positions of SZ map and positions of galaxies. And if this gas sits in a certain redshift region, cross correlation will exist. Otherwise, it vanishes, right? So in this way, you extract the redshift information. So for the SZ, we use all the Planck data as well as IRAS, infrared data, to get some handle on dust. Because to extract SZ, you have to be really careful about contamination of the dust in dusty galaxies outside of Milky Way. And for galaxies, we use 2 million redshifts of galaxies and quasars from redshift 0 to 3. Okay, so we get tomography all the way up to redshift 3. All right, now what we measure is the pressure density cross correlation. And we divide that pressure density, galaxy density cross correlation by the matter power spectrum and bias of galaxy that you measure and number density of galaxy you measure. And this will give you like a pressure biased mean pressure. It's like we don't measure just mean pressure. Okay, we measure pressure at the locations of cosmic structure. So this is the density weighted pressure. Yeah. So that's B times P. So this is how measurement looks. So this is the ray field that I just showed, and it's flat. Yeah, flat. And this is the region we extracted the signal. And basically, so this is the signal extracted from the somewhat larger scales, and they're completely flat, right? So we kind of trust these measurements because we know what we're doing here. So that's a robust measurement in all redshift bins. And then here is the extracted signal. So you see that this x-axis is now redshifts. And if you look at 100 gigahertz, where intensity should be negative due to Snell-Zerodovich effect, it's negative as promised. But as you go to higher redshift, somehow it's no longer negative. And this comes from this contribution from dusty galaxies that emitted, the thermal dust emits light, right? And 140 gigahertz, 143 gigahertz, it's less negative, but somewhat negative. Then dust goes up, cosmic infrared background. To 17 gigahertz should be null. There shouldn't be any SZ, but you do see some signal here. That's again CIB, dust emission, and so on. Okay. So we do the simultaneous modeling of SZ and CIB to extract the SZ signal. And this is the now spectral energy distribution of the signal we're seeing. So redshift 2.1, we get SZ here. Actually, this is the zoom in of this. Here, it's negative, but then quickly you look, you get something like a black modified black body for dust emission. So we do this decomposition to separate SZ and thermal dust emission. So this is the first main result. What we measure is the pressure, but biased in the overdense regions. So this B is a factor that multiplies the mean pressure. So this is not yet mean pressure. Okay, this is the biased version of it, and this is the direct outcome of our measurements, completely model independent. And so you see these data points, which let's see, black is our measurement, and then there are other measurements here, for example. They are all based upon the photometric redshift of galaxies and not spectroscopic redshift. And this is the first measurement that used the spectroscopic redshift. Therefore, all these data points are independent. There's all this black. And this pink region is a kind of model. You don't really have to take it seriously, but they go through the data points very nicely. These are upper bounds because of the cosmic infrared background contamination. We don't trust these measurements. But it's actually very interesting to extend this to higher redshift to really see what's going on here. Because our understanding of pressure evolution seems not converged yet in this region. Okay. For example, if you run different cosmological simulations of galaxy formation, they differ here. And these measurements can actually select which simulation is correct. So I'll get there later. Now, what about this B? So this B is this. Now, let's say you have hot gas in dark matter halos. And dark matter halos trace underlying matter distribution in a biased way. So there's a bias of halo that you can compute from the cosmological n-body simulations. Then it's weighted by pressure. Okay, so pressure is mass times temperature. And the Vilero theorem tells you that the temperature goes like mass to the 2/3. So mass times temperature will be mass to the 5/3. If everything is kind of self-similar. But then there's a observed correction to that 5/3 scaling. That's 0.12 coming from X-ray observations. So we correct that. Then we get this halo model, kind of calculation of pressure bias as a function of redshift that goes up. Okay. Then once you make that correction, you debias the measurement, and you get what you want, namely omega thermal, yeah, 2 times 10 minus 8. And you can also translate that trivially into the density weighted mean temperature, because what you get is density times temperature. It's a pressure. So density times pressure divided by density mean would be the density weighted temperature, and that's 2 million degrees today. So that's what you get by Googling gas temperature of the universe, yeah? And evolves over time. So redshift 1, and it will be 3 times, increases by 3 times temperature, yeah? So this is the first measurement of evolution of temperature in the gas of the universe. And we only have upper bounds here. Yeah. All right. And if we know the mean temperature of the universe, we can also calculate, right? If you average over the full sky, how is the CMB black body is modified, right? We all hear that the CMB is a black body. But because of this distortion, even if you average over the full sky, you will get a distortion. And current upper bound on this Compton Y parameter that characterizes the strength of the SZ is something like 1.5 times 10 to the minus 5. Our measurement suggests that if you go 10 times fainter, you'll see this distortion. Right? So this is our prediction, well, actually measurement that suggests that if you can improve Phyla's measurement by factor of 10, you ought to see this deviation from black body. It's a guaranteed signal for the future space mission to do the spectral distortion measurements. Yeah. And previously, we all used theoretical model to compute this. Now we have the data to really show that this is what we get. Yeah. Error bar is something like plus or minus 10 to 20%, depending on how you characterize it. So where did all this thermal energy come from? And of course, you know the answer, actually. If you open up any textbooks, it says something like, large scale structure forms and matter density fluctuation collapses and gravitational energy is now converted to thermal energy through shock heating. That's a textbook description. And everybody believes it, okay? There's nothing wrong with it. But have we actually ever tested this quantitatively in observational data? To my knowledge, answer is no. So let's do this. Energy conservation calculation, right? So we first calculate a gravitational energy density, and we compare that to the thermal energy that we measure to figure out energy conservation in the universe. So indeed, when you try to reproduce my SZ measurement, clamp comes in and shock heated and so on, right? So gravitational energy and kinetic energy. Gravitational energy goes into kinetic energy goes into thermal energy through shock heating and so on. And if you do more sophisticated simulations like illustrative simulation, indeed, redshift 2 and as matter clamps, gravitational energy gets shock heated, converted to thermal energy. That's the temperature. Yeah, is this correct? All right. So if you now open Jim Peebles' textbook in 1980, he has all the answers, right? So a gravitational potential energy density, W, times m, which is the mass, okay? Then, so this W is the gravitational potential energy per mass. And if you multiply that by the total mass, you get the gravitational potential energy. This is actually nothing but density times potential integrated. So if you go to Fourier space, then your gravitational potential energy is nothing but potential density cross correlation power spectrum, which is related to density power spectrum by Poisson equation. This is something you can calculate, and this is exact in the limit of non-relativistic, non-relativistic subhorizon limit. So no assumption of Gaussianity or anything. This is exact. So you can plug in your favorite nonlinear power spectrum here and compute this exactly. So you know what gravitational potential energy you have. And let's compare this to the thermal energy. All right, there you go. So x-axis is redshift. Vertical axis is the co-moving energy density of either gravitational energy or thermal energy. Let's start with this. This is the total gravitational energy density available in the universe. It's huge. Okay. Then, because our measurements are basically dominated by gas within dark matter halos, that's the gravitational energy density in halos you can compute. So it's about 1/3 of total energy densities, gravitational energy densities. Now, what we measure, however, is the baryonic part of the total energy in gravitational potential. So you have to multiply that by baryon fraction. So omega baryon divided by omega matter. And that blue now is what you have as the source of gravitational potential energy that that's available for shock heating. Green. Blue is our measure of the thermal energy densities. If this exceeds green, something is terribly wrong. And it isn't. In fact, it's really beautifully parallel, and it's 80% of your gravitational potential energy. Energy is conserved, so 80% of gravitational potential energy was converted into thermal energy by shock heating, but not 100%. Yeah. So what is the rest? That's non-thermal pressure. Well, obviously, because thermal was non-thermal. What is the non-thermal pressure? So let's say you have a stuff falling into galaxy cluster that gets shock heated, but you also have kinetic energy, just bulk energy, bulk kinetic energy. That's not yet thermalized, right? Not this shock heating doesn't occur instantly. So, but if you wait enough, right, wait long enough, all of this non-thermal kinetic energy will be dissipated in heat and 100% thermalization. But galaxy clusters are not in isolation. They constantly accrete matter from surroundings. So this constantly injects non-thermal pressure into the halos, and that's what we see. This is something you can calculate theoretically. We developed the theoretical framework for it, and just matches exactly. So this is good, right? So we actually understand really in a detailed manner how energy conversion is working in the universe. Now, if you go back to this, there's a lot more kinetic energy available actually than in the universe, right? How do we get access to it? Kinetics near the Ricci effect, or something that you can get from bulk motion of velocity. Okay, you have velocity reconstructions of galaxies nearby. You can try to compute kinetic energy of everything in the universe. Then you can do the test of where did it go, right? But so far we are still confined to this fraction of the gravitational potential energy available for heat. Is it good for anything? So far, I think I'm very proud because this really beautiful. No, it's energy conservation. Yeah. But is this useful for anything? Okay, let's see. So if you can simulate, right? So Klaus Dolag, this magneticum simulation, it's one of the state-of-the-art hydrodynamical simulations of cosmic structure formation, including AGN feedback, supernova feedback, everything you want it. Then you can just compute this from simulation and compare to the observations. It agrees quite well, actually remarkably well, because this particular simulation was never tuned to reproduce any of these measurements, right? So it's nice. But then here, our results are only upper bound. If you use different hydrodynamical cosmological simulation, like illustrious, they agree here. They're completely different here. So if we can extend these measurements to higher redshift, then we can use this to test the cosmological hydrodynamical simulations in a very easy and robust manner, because the measurement is relatively easy to make. Now, you can also look at the mean temperature to test. We had this bias factor. How do we trust it? And if you can compare the temperature we inferred from the data using this prescription for bias in pressure, and if you compare to the temperature you measure directly from the simulation, they agree. Yeah, so it's very good. Seems like we understand something, except this high redshift part that's yet to be tested. All right. So let me say that, okay, this is very nice. And energy balance seems to work in the universe, okay? But for me, this is actually 20 years of homework at Princeton. So Chen and Oestreicher ran one of the very first cosmological hydrodynamical simulations and show how temperature evolves in the universe. And so that was based on Renew Chen's hydrocode. Now, Willy Penn wrote his version of hydrocode using moving mesh. Yeah, I think he was the first one to use moving mesh for cosmological hydrodynamics. So now Volker Sprengel has Aleppo code, which is a moving mesh, but he was a pioneer. We have a president here. And we finally measure this, okay? So let me show you. Chen and Oestreicher, so famous paper. It's 10 million degrees, right? So we can rule out this. I mean, it's unfair now, but how useful is our measurement? You rule it out, right? Galaxy formation simulation. I mean, there was no way to see whether this was correct at that time, but now we have means to correct it, to really see if that's true. That's 1999, then 2000 is our paper. And I tell you that not only the gas temperature in the universe, but also human evolves over time. 2001, 2015. This is yesterday. Yeah. David's glass is changed. Yeah. Yeah. This to that. Yeah. And this is our prediction. No. At that time, we had to explore open CDM, loud matter CDM, standard CDM, right? And if you look at the number at the redshift 0, it's 2 million degrees. It's not bad. Yeah? So yeah, I'm very satisfied. Okay, thank you very much.
Great, thank you for that great talk. Do we have any questions? Maybe we start over here.
No, that was fantastic. I'm curious if you can speak to physically why the simulations vary so much among.
Here.
No, not. I mean, not this simulation, but the.
Yes.
As you're talking about, like, there's a lot of agreement
Yes.
at late times.
Yes.
What is the like?
Yes.
Why are some simulations putting more or less energy into the thermal?
It's feedback.
So it is. It's really okay.
Yeah.
Great.
Yeah. In fact, cosmological parameters for feedback is different for magnetic arm and illustrious. So I think that's the reason for the difference. We cannot be 100% sure, but that's something we are investigating now. That's likely the result, because otherwise energy has to be conserved, right? Gravitational energy, shock energy, that has to be universal for all simulations. Only thing that's different will be feedback. Now here, Renew chain simulation and our simulation had exactly the same cosmological parameters. So the results are very, very different. And I think they put too much feedback in this simulation. So that's why, because otherwise energy is not conserved, no? But here you're extracting basically energy from nuclear, right? Stars, defeats supernova. So that's a much more efficient way of converting energy into heat. So that's I think that's the cause.
Do you think that, I mean, it's going to be a lot of work until you can sort of push these kind of very comprehensive measurements all the way out. In the meanwhile, do you think that some of the stuff that you guys are doing with individual systems will have enough leverage? Like if the variation really is that large, are there some sorts of extremes where you would just never expect to see it with some feedback models versus others? Right, like if you look at a galaxy cluster at a redshift of 2,
right,
is that potentially discriminatory?
Yeah, I'm not so sure, because the individual variations of clusters are very large. And I think you can always find counterpart in simulations, but average property, right, is harder to change. So that's why this measurement is so powerful. It's the average global property of thermal energy in the universe. So therefore, I'm not so sure whether individual measurements like we made using ARMA will be decisively ruling out some of the simulations.
I think David was next.
So many thoughts. I have a million questions, but I can't do that. But one thing I would say, I sort of disagree with your conclusion about which sign that energy conservation should have, because of course there could be other sources of energy input.
Yeah, feedback.
And I think that's an extremely, so that makes this a very fundamental measurement. So let me ask you, on the side of extremely fundamental, imagine that the dark matter had a very small cross section with the baryons.
Okay.
I believe that in the long run you would heat the baryons further if the baryons are lower in mass than the dark matter particle fundamentally. So if there was even a tiny cross section, I think we would get information both about the dark matter mass and the cross section.
Yeah, that's very interesting.
Have you computed those limits? Because
no,
seems
but we'll do it.
Yeah, okay.
That's really cool. Thank you.
Yeah, good. Great.
David?
17% plus or minus something of energy being non-thermal.
Yes.
Now, the non-thermal, I can imagine being in at least 3 different forms, kind of bulk flows, magnetic fields, cosmic rays.
Yes.
The latter two I'd expect to be more centrally concentrated in the halo. The bulk flows, the non-thermal bulk flows outside.
Yeah.
Now, are your ALMA measurements or even some of the lower resolution TSC measurements good enough to measure sort of the halo, the galaxy TSC cross correlation, so that one gets the angle independence to see that?
Like a to very center. I think, not very center though. But we could go in there. Yeah, that would be one halo term. Yeah. That's right. Yeah, yeah.
And I think that the different physics would give you different forms.
Yeah, indeed. I think, that's good. I think it's good to test that using our measurement too. Just to note that cosmic ray and magnetic fields can be proved some other ways using radio, further rotation. So they all show that energy density magnetic field in cosmic ray are really a percent level compared to thermal energy. So at least we know this from other measurements. But indeed, it would be nice to check that here as well. I'm not sure we'll be able to really see it, but if there are cosmic rays, then there are non-thermal SZ whose shape is different from the thermal SG. So we can put a bound.
And the expectation is the bulk flows are more important.
Yeah, that's right. That's correct. Yeah. Yes.
Great. Thank you. Will? Could you use the seat mic maybe?
Sort of following up on that question, looking at these one halo terms as a global measurement, but can you push your individual measurements of clusters and looking at the sloshing, for example, to account for the kinetic part of the missing energy? Or is that just impossible because you're just doing it one by one and they could all be some special case of a very out of equilibrium cluster or something?
I suppose, for example, what is the available gravitational potential energy for that particular cluster, right?
Yeah.
Exactly. I think that's very hard.
Yeah. Okay.
Because density fluctuations varies. Yeah. Kinetic energy in sloshing. Yeah. So this will be induced by perturbers, right? So that's yeah. I mean, I suppose it's related to gravitational potential energy as well. Yeah.
Great. Yes, please.
Another source of heat around some of these regions could be AGN, like active galaxies. And is that something that could be studied, like particular SC signals from known AGN sources?
Good. So let's see. Indeed, Renyu Chen's simulation also showed that the feedback can push this above, right? And that's not happening here. So that's good. Now, therefore, AGN feedback will just shift this, I guess, upwards a little bit. Yeah. And now, how do we really test that, right? So simulations is one way. Indeed, simulations with different AGN feedbacks predict different amount of thermal energy. Yeah. Now, but I think you're asking, for example, targeting individual galaxy cluster, can we do something about it, right? And yes, AGN gives feedback, which can be individually detected by SZ. Yes, indeed. How do you know, fraction of that is due to SZ, the AGN, or shock heating? That again, I think it will be harder to distinguish between them individual. Well, if we see jet, but then jets usually clear gas, and but I guess surrounding it, yeah, it's an interesting. For example, this Phoenix cluster has actually both this RxJ 1347 and Phoenix cluster. They both have NGNs at the center. And we see jets and so on, but so jets clear up gas, create cavity and so on. Nothing here. So I think
it could be because the thermal bubbles are much further out.
Well, I think
those could be megaparsecs out.
I think that's because of the sensitivity of our measurement. I think this energy injection due to jet is below our noise level, I think. But so its bulk is still really the gas coming from shock heating. But it's an interesting question to see how long we should integrate to really see, right, impact of the agent feedback in the SZ. And I think, yeah, I mean, this is a gigantic cluster, so jet is not going to go beyond. But if you go to group scales, then you will, right? So I think Atacama Cosmology Telescope, they do the stacking of 10 to the 13 solar mass galaxies to see what is the extension of gas, and that's bigger than you might think naively. So that kind of hinting the impact of agent feedback.